Thanks a lot. And first, I would like to thank the organizers for this meeting. I'm really enjoying being part of it. It's very interesting. And today we'll speak about a project started in collaboration with Antoine Renaud, who was my PhD student some years ago, and we collaborated with Louis-Philippe Nadeau. And I went back to this problem recently, again with Louis-Philippe, and this time with a master student with him. I was collaborating with them. Okay, so let's start with the stratosphere. If you don't know what it is, we live in the troposphere. This is where the weather takes place, where you see the clouds. And the stratosphere is above. The equator, it's around, let's say, 15 kilometers. It's where the boundary is where the plane fly. And so there is no clouds in the, almost no clouds in the stratosphere. And what you need to know is that by the name of it, is strongly stratified. It will be very important in the remaining of the talk. So it's hard to measure winds in the stratosphere because it's very high. And a source of information went from the huge explosion of the Krakatoa volcano at the end of the 19th century. So huge that the ashes were up to the lower stratosphere. And then it was observed that those ashes were drifting westward. So it was called the Krakatoa easterlies at the time. But another way to measure the winds there is to send balloons. So it's a recent picture because there was a recent campaign of measurements around the equatorial area. And but balloons were sent near Lake Victoria, so again close to the equator, at the beginning of the 20th century. And then the winds that was observed was in the other direction. It was eastward. Okay, that was strange. And the puzzle continued when there was continuous observations in Singapore, I think, with balloons that started in the 50s. So you see the years here, and you see the lower stratosphere from 20 to 30 kilometers high. And in color, you see the magnitude of the horizontal velocity that switch between roughly 30 meters per second in one direction. Red is eastward, and then in the other direction, westward. So that was very puzzling at that time because it's a spontaneous emergence of an oscillation that seems not too much correlated with seasons because the period fluctuates, but it's around 26, 28 months. So there is a reversal each 14 months. And so when there was, say, enough data to see the reversals, an explanation came in a few steps. First, by a paper by Lindzen and Holton, then Holton-Lindzen and Plumb found the minimal ingredients to explain those oscillations. And I want to stress that this phenomenon is located around the equator. It does not happen at mid-latitude. Also, there can be connections between extratropical dynamics and tropical dynamics. So that seemed to be something well understood and explained in textbooks. But surprise came in 2016. So there are two papers, I think, that explain noticed this strange appearance of periodicity disruption. And if you read the abstract, so it explained that it was disrupted, and then a return to more typical QBO behavior within the next year is forecast. So the possibility of more frequent occurrences of similar disruptions is projected for a warming climate. And in fact, in 2020, there was again a disruption. So that's the main motivation of this presentation. And those are three big questions. First question, is there other dynamical regime that's possible than those regular oscillations? What are the relevant parameters for those oscillations? And in the first place, now that we see that it can be disrupted, those oscillations, why it has been so robust before? So the first two questions, let's say the basic ingredient are fairly well understood. Also, I think it's really deserves a second look, now that we see that there can be different regimes. And the third question, I'm not sure the answer is clear. No. So the outline of the talk will be first, and perhaps it will be the most important thing. I would like you to present the model proposed by Holton-Lindzen-Plumb, because I think it's a very nice dynamical system. Then I would like to show that in this model there is a quasi-periodic route to chaos with interesting regimes with respect to the stratosphere, perhaps. And then I would like to go back to the third question and to discuss possible synchronization effect with the internal dynamics in this framework of a simplified model. So, okay, let's start with the model. And the three ingredients that were identified by Plumb were, first, you need stable stratification, because then you can propagate waves owing to this stratification. Those waves, they are internal gravity waves. We heard a lot about those waves those three days. So the stable stratification here will be stratosphere. Second, we need a wave source somewhere, wave generator, and it will be the troposphere. All the equatorial, complicated equatorial dynamics, deep cumulus, for instance, that bump into the lower stratosphere or that release heat with condensation. And the third important ingredient is confinement in the vertical plane. In all the models I will present, we'll describe a vertical plane at the equator. So it's a huge simplification, but it can be motivated by the fact that rotation confines in different ways motion here. And there are interesting questions about this confinement. Peter Haynes here worked a lot about why the phenomenon is confined here. But from now on, we will assume it is confined. We simplify the modeling. Okay, then after the work of Plumb, he and McEwan proposed an experiment that get those three ingredients. So it's okay. I'm cheating a bit because the experiment was the other way around. The membrane was above, but it doesn't change anything from a theoretical point of view. So you think things upside down. But the important thing is that you see the three ingredients. So you replace air by water, but that is stratified with salt. You replace the tropical clouds by the membrane that is oscillating. And so the configuration is here is two cylinders. So it's almost two-dimensional because the flow is confined between the two cylinders here. And actually, recently, there was the experiments, from what I've heard, is really difficult to reproduce, but it was reproduced several times. This movie is taken from this website when they have many very nice examples of geophysical phenomena. And so a very thorough analysis of the transition, both experimentally and theoretically, was proposed by Benoît Sémin, François Petrelis, and Stéphane Fauve. So let's look at what's happened in the experiments.
You made water stratified by temperature?
By salt.
By salt?
Yeah. So if you force sufficiently weakly, you just see some oscillations, standing waves that correspond to an standing internal gravity waves. And if you force sufficiently strongly or faster, so I think the film is accelerated. You see there is a symmetry breaking. And if you look at a given altitude, you will see the reversals, and you will see that there is a downward propagation of the phase, which is the hallmark of these quasi-biennial oscillations. So I really find it quite impressive. And actually, I learned about, I saw those movies probably when I was at the summer school here, some time ago. Okay.
There is rotation here?
No rotation. So rotation is important for the Earth because it confines motion at the equator. But here you confine motion between two cylinders, and you can play with the thickness between the two cylinders because it changes friction. But yes, it's important to be in some way two-dimensional. And from a theoretical point of view, it's perhaps the archetype of a wave mean flow interaction problem. At least it motivated a lot of theoretical results to explain this phenomenon. And what is interesting with respect to this workshop is that actually one of the first studies trying to explain the phenomenon, they modeled the eddies, the fluctuation, with down gradient viscosity. And it didn't work at all to explain the emergence of the QBO. So the first explanation came after, when Holton-Lindzen used recent result at that time from Brooker and Bretterton to explain how internal waves, when they reach their critical levels, so altitude where the mean velocity is equal to the horizontal phase speed of the waves, they manage to transfer the moment to be absorbed and to transfer the momentum to the mean flow. And this effect, this single effect, explains the downward propagation of the front. And from a practical perspective, I think it's a very nice example of a large-scale phenomenon, so planetary scale, low frequency, in the sense that it is a 2-year scale, that you do not get if you do not represent the effect of small-scale high-frequency waves. And there is a huge separation time scale because the typical time scale for the oscillation of internal gravity waves is the buoyancy frequency. So G is gravity, D0 is the gradient of density, Renaud is a reference. And this is the time scale of oscillation of a particle because of buoyancy. If you take the particle, you displace it, and then it oscillates at this frequency. And in fact, in climate models that 20 years ago, almost none of them was obtaining a QBO. It's no more the case. And one of the reasons is that, there are several reasons, but one of the reasons is that they now parameterize in those models the effect of the waves, their feedback in the momentum equation, even if the waves themselves are not resolved. So let me first show you the reduced model by Holton-Lindzen-Plumb, and then trying to explain piece by piece what it means. So this is the reduced model, and the aim of the model is to describe the temporal evolution of the horizontal wind, u, average over the equator or over the azimuthal coordinate in the experiment. And it's a function of time and a function of altitude, z. And so it's 1d plus 1 time direction PDE, integral differential, because you get this integral here in the exponential. And okay, I will go through the different steps to get this model, and then present you some of the solution that comes out from this model. So my starting point today it will be incompressible Boussinesque fluids. So you may think, and you will be right, that it's not very relevant for the atmosphere because of the exponential decrease of density. And in fact, you can derive a version of this model with the inelastic framework that take into account the variation of density. But for clarity, I think it's good enough to start with incompressible fluid. And we saw already several times those equations, but there are a few details I want to insist on. So those are momentum equation, Navier-Stokes with fields, the buoyancy fields that is advected by the velocity field. And importantly, I add a damping term which represents Newtonian cooling that repeals the stratification to a base profile. So N, capital N, I repeat, is the buoyancy frequency. Again, to simplify, I will consider it as a constant in the remaining of the presentation. And same for this Newtonian cooling coefficient. It will play a very important role because it will be the main parameter that dumps the waves, this repelling toward stably stratified profile. It will be more important than viscosity that will only play a role for the mean flow. Then I consider the configuration of the experiment where we force a boundary as a stationary wave, so the sum of two contra-propagating waves. Epsilon will be the amplitude of the boundary variations, omega at frequency, k the horizontal wave number. And forget about the cylindrical geometry. It will be periodic in X, and I will consider semi-infinite domain in Z direction, and then I will also discuss finite size effect. So if you count the parameter, you may see they have 6, and now you look at non-dimensional parameters, there are 4 of them, and the good thing is that you get 3 of them that are small, and you can organize them in that way where epsilon k so control the amplitude of the forcing, and you want this to be weak because you want to be able to do some weakly nonlinear analysis. It will be a quasi-linear approach to get the model. So this parameter is small for this. Then this parameter is small, and it simplifies your life because when it is small frequency corresponds to the hydrostatic limit in the equation. And this parameter is really important. It's also small, gamma over omega. It's not obvious at first sight, but it's a bit like a Richardson number because it will control the spacing between typical variation of the velocity field and the wavelength of the internal gravity waves. It is controlled by this parameter. The idea is that the wavelengths will be related to the frequency, the vertical wavelengths will be related to frequency, and gamma, the damping, will be related to the mean flow variation. And so you get 3 parameters, and at the end we will get a model with the 4th parameter that I will call a wave Reynolds number that will control the transition between different regimes. So the important thing now is that we want to describe an equation for the mean flow that I define just here as a zonal average over the x direction. And I'm cheating a bit because you also need to make some small time averaging over a few oscillation period, say. And wave will be just a fluctuation around this mean flow for all the fields. And okay, you can apply this filtering operator to the horizontal momentum equation. So far there is no approximation. You take advantage of the periodic geometry and you get just the temporal evolution is given by viscous term minus this term, which is the main important point of the model. This time corresponds to Reynolds stresses, convergence or divergence of momentum flux. And all the game is to find a closure for this term. And this closure will be a parametrization for internal waves in what follows. And so the strategy to get this is it's a quasi-linear one analysis. So you start from an initial set of equations, you linearize around the frozen in time mean flow, so you assume a scale separation. Then you compute the stationary wave field. So it needs to be stationary. There is again an hypothesis of scale separation. Then you compute, once you get the wave fields, the Reynolds stresses, you plug it into this equation, and you hope that the mean flow evolution will be slow enough. So in the model I presented you now, I will skip the derivation, I will just show you the results. But I want to insist that in this term there will be 2 important physical effects. One is streaming, wave streaming, how waves can generate momentum for a mean flow. And the second will be enhanced dissipation or reduced dissipation due to Doppler shifting. So let me say what I mean by this. But before this, let's look at a simple case. So forget about the stationary membrane. Consider a membrane that is a propagating wave, like this in the experiment. And let's look at the isophases of the waves. So this is the waves emitted by this membrane. Forget about mean flow. Say there is no mean flow. Forget about dissipation. There is no dissipation. what is important about those internal gravity waves for today is two things. One thing is that the frequency sets the angle of propagation. So omega tells you what's the angles of the wave phases here. And the other thing that is important is that you get the transverse waves because of the non-divergent velocity field. The velocity in blue is perpendicular to the wave vector, wave number vector. And so I draw here velocity fields there and there, and you can see that there is a positive correlation between horizontal velocity and vertical velocity, which means that you push towards the right with these waves. But because there is no dissipation, you take the gradient in vertical direction is 0, so you will not create a mean flow. It's called the non-acceleration theorem. Just the observation that when you get no dissipation, you have no force generated by the waves on the mean flow. But now we have dissipation in this case, and this is where the effect of streaming comes into play. If you have dissipation, the amplitude of the waves is reduced here, so the value of this guy is smaller here than here. So there is a gradient of of momentum flux, and there is a typical scale. And keep this in mind because this vertical scale is key to the problem. This vertical scale of attenuation is 1 over the dissipation coefficient, gamma, damping rate. Omega is proportional to the square of the frequency, 1 over k, the wave number, and stratification. It's important because at the equator there are different kinds of waves, and depending on those waves, you can play with this attenuation length scale. And so in that case, and this is the first piece of the model, you get that wave attenuation drives horizontal winds in the direction of the horizontal phase speed of the wave. So horizontal phase speed is omega over k. Okay, that's one thing. And then when there is a mean flow, within the scaling I proposed before, you can use WKB to get, it's the same formula as before, but generalized when there is a mean flow that varies at scales larger than the wavelengths of the internal waves. And then let's consider a simple case where the mean flow is constant. And then you get just Doppler shift, because when the mean flow is constant, you replace time derivative by time derivative plus transport term, u times derivative in x direction, which corresponds to a shift of omega to omega minus k times the mean flow. So this is the Doppler shift effect. And what you see is that the Doppler shift effect changes the attenuation length scale. So there are two ways to do it. If the mean flow is in the same direction as the horizontal phase speed, there is an amplification mechanism because you decrease the attenuation length scale. So you increase the gradients of the momentum flux. And so this is a positive feedback mechanism. Another point I want to stress is that something peculiar happens when you reach the critical layer, because all the waves is absorbed no matter how small the dissipation is. And this is very important because the velocity cannot exceed this value. The velocity generated by the membrane will never exceed, within this model framework, the value of the phase speed of the waves. Okay, last things about the physical mechanism is that with the same Doppler shift effect, if you consider a mean flow that is in the opposite direction to the phase speed of the wave that is generated, look again at what is the attenuation length scale. In that case, it is increased. So the gradient is 1 over this length scale times the momentum flux generated here will be smaller, and which means that we dissipate late, so you will have a weaker force, but, and this will be very important, the wave will propagate higher in the stratosphere. So I sum up. If there is a mean flow in the same direction as the waves, there is an amplification. If the mean flow is in the direction opposite to the waves go higher in the stratosphere. Okay, so now let's come back to the experiment where there was a standing wave. a small miracle happens. I don't know why, but if you take a collection of waves, there is no cross correlation. Maybe there is an obvious reason, but I don't know which one. And so you can decompose the momentum flux into two components: the one generated by the leftward propagating or eastward propagating waves, and the one generated by the rightward or westward propagating
What do you
waves.
mean there is no cross correlation? It's like somebody proved it, or it's just empirical fact?
No, it's I don't. It's when you compute it, you find it.
Just empirical fact, yeah?
I don't know what you call empirical. Is you compute the flux, the correlation, the cross correlation between U minus and U plus at 0.
So this is around one single wave, because a single wave is an exact solution of the nonlinear.
You can do it with the multiple waves, so it's more general than this, I think, but it's at lowest order in the development, so maybe if you go to next order to the small parameter, I guess it falls down.
That makes sense.
And what will be important in the following is this quantity F naught that I will call wave forcing, is the amplitude of the momentum flux generated by either of the waves, eastward or westward propagating waves. Okay, so you can relate this parameter to the frequency, buoyancy, wave frequency, buoyancy frequency, and amplitude of the forcing. So now we get all the piece of the original model of Plumb. And it's quite instructive to look at the non-dimensional version of this model. It's all well explained in Vally's book, actually. But I tell this to you because really it explains so much about the QBO just by this. So you rescale U by the phase speed C, and C, as I told you before, it sets a limit, a bound to the amplitude of the QBO. And actually, if you look at the waves that are in the stratosphere and you look at the value of the mean flow, they are similar. The vertical length scale is scaled by the attenuation length scale. And again, if you put number, it gives a good order of magnitude. Then also very important, the time is scaled by typical time scale, which is phase speed times attenuation length scale divided by wave forcing. And this is very important because it means that the typical time of the system, the QBO time, is 1 over the amplitude of the waves, and to the square. So it was a central result, I think, of Lindzen, Holton-Plumb model, that the waves set in some sense the amplitude of the time of the oscillations. So once you have your model in a non-dimensional form, you see that there is only a single parameter, the wave Reynolds number, that compare, in some sense, the forcing F naught to the viscosity. But there is a second one, parameter, which is hidden in the boundary condition, a geometric parameter that compare the attenuation length scale to the total size of your domain. So in the experiment, it will be the size of the experiment. In the stratosphere, it's not so clear because there is a mesosphere about the stratosphere. So well, we can discuss this later. Let's think then about the experiment here. So, okay, for the first part of the talk, that was about the model. And now I would like to show you some solution, numerical solution of this model. There are few analytical solutions, but there are steady state solution or solution near the first bifurcation. And I want to put emphasis of other states. And first, let's go back to the movie just to reinterpret what we saw. So in the case where nothing happened, so that case, you can really see it as there is a leftward moving wave, rightward moving wave, one push toward the left, one push toward the right, and when the flow is sufficiently viscous, they compensate each other, and it's a stable state. So the rest state is always a solution, but it is stable only for sufficiently large viscosity. And then you you can easily break the symmetry, forget about viscosity, put a small mean flow, so the forcing will be amplified in the direction of the mean flow here. Here, the opposite effect will happen, the wave will go higher up in the experiment, in the stratosphere, so it will push more toward the right, and this is what happens with higher forcing. Here, you create a mean flow here, a mean flow in the opposite direction below, and then the front descent. So I'm cheating a bit because I'm showing you the experiment. In the experiment, the dissipation comes from viscosity. In the model and in the stratosphere, one of the main player for the dissipation is really this radiative damping, this Newtonian cooling effect. And now I come back really to the model with radiative, with Newtonian cooling. So this is the limit cycle that you get once you go through the first bifurcation. So qualitatively, you get the descent of the phase and the alternance of the eastward-westward jet. And you can check that the period scales as expected with the amplitude of the waves. But then you can go further with the control parameter, the wave Reynolds number. And actually, it was observed way before us by a paper by Kim and McGregor in a slightly different setup because it was motivated by the solar tachocline. So boundary condition was different, but really it was this model in a different set of parameters. And when you increase the wave number, you get a quasi-periodic route to chaos. First, you switch from a limit cycle to a torus with two incommensurate frequency. You increase nonlinearity, so on the torus you can have phase synchronization. You get those, you going back to limit cycle, and then sometimes you get three-dimensional torus, but it's unstable and you end up in two chaotic states. And the point I want to emphasize is the structure, the vertical structure. Each time you get a new kind of state, you have the excitation of a mode. We have more complex vertical structure with smaller, faster reversal embedded into a deeper, smaller reversal. So this was an observation, and we were a bit puzzled by this. And this is the phase diagram here in a Poincaré section when to see the transition from the rest state above to the chaotic states when increasing the Reynolds number. Okay, and then we come to a typical question with those systems that you observe a funny dynamical feature in a simplified model, but the question is that can it be robust to more complex model? It's not always obvious. So we did only a small step toward this direction here. We look at the starting model before the quasi-linear model introduced the two-dimensional Boussinesq stratified fluid, so it's fully nonlinear. And indeed, in this case, we observed a qualitatively similar route to chaos. We also had preliminary simulation on the beta plane. I do not show it now, but this will need to be pushed further, I think, to be sure the bifurcation persists. And yeah.
So in these simulations, you've got a relatively low Reynolds number. So is the critical dynamics the same as in the original model?
It's a good point. Actually, what happens in the simulation, in the way we force. So in the model, we control everything with the forcing amplitude, while in the simulation, there is some breaking, some strong linearity at the forcing, and then there is an effective forcing that we can diagnose from above, higher up, where it behaves more linearly. So we had a hard time to interpret the relation between these Reynolds to the one of the previous case, and I still don't know actually what's the link. But it's an important point. So well, it doesn't change the fact that qualitatively we observe it, but the role of nonlinearity in the lower part, it's unclear. Yeah. So now I would like to discuss about those successive bifurcation. And first, I will redo what others have been doing before. So Plumb in his paper, he linearized those equations around the rate state, and he looked at the inviscid case, and the result is quite interesting because you find an exponential increase at each altitude, but the most unstable altitude is the one at below, so it is in the inviscid case. And it was to understand the destabilization. And then more recently, Benoît Semin, in his paper, looked at the case with viscosity, and he was interested to describe details on the first bifurcation. So he looked for eigenmode of the linear operator, of the linearized dynamics. And he looks for particular value of the parameter where this sigma becomes as a real part, which is positive. So he computed this point here. So the color here, orange and black, just means that you get in black eigenvalues that are imaginary, oscillating modes, either stable or unstable, and orange, they are purely real. And okay, so in that case, it corresponds to a supercritical of bifurcation, and you get the imaginary value of the eigenvalue that gives you the frequency of the oscillation of the bifurcation. You can play with the model, find a subcritical of bifurcation. It's a nice dynamical system, but I want to emphasize something else, is that if you look at the other unstable eigenvalues, the secondary one, then there is something a bit puzzling. At first sight, I saw it was a pure chance of Hadar, because to make things correctly, we should do Floquet analysis around the oscillating states to know what are the secondary bifurcation. But then look at this second bifurcation with the Reynolds number, and at the eigenmode of the linear dynamics. So the second bifurcation occurs when an unstable, third unstable eigenvalue of the linear problem arises. And then again, you skip one eigenvalue, nothing happens here. And the next one, okay, I did here, it's a bit further, but it's not too far from the transition. Okay, we just observed it, and the more you go higher in the eigenmodes, the more oscillations you get. And okay, is it by chance to see it? We consider the full phase diagram by varying the two parameters, the geometric parameter, comparing attenuation length scale to the total height, Reynolds number, and it turns out that we really get the transition lines corresponding to the appearance of unstable eigenmodes for the linearized dynamics around the rate state, which is a bit surprising. So far, I have no explanation for that. Maybe you have one. And so I will finish this part with the main message to take home is that the secondary bifurcation towards non-periodic solution appears through the excitation of high vertical mode. And why it is interesting, I think. So you see the mean wind profile evolving. In color, you see the forcing of the leftward and rightward waves. And what you will see in some times is that in some regime, you get these patterns that qualitatively looks a bit similar to the disruption of 2016. But I'm not able to say more than this at this stage. So I will stop for the search of chaotic regime and description of chaotic regime for now. And come back to the last question. Why has the QBO been so robust before 2016? And then it will be, again, quite descriptive. But before this, I like to mention several reasons why we should expect it to be periodic. First, in the model, we missed something important, is that there is a mean motion in the stratosphere, meridional motion, but that you can put into the one-dimensional model as an upward velocity. And when you do this, it's quite easy to come back to periodic regime by tuning the parameter. So you have one more non-dimensional parameter to play with, and you can have all the states you want to. Then there are other phenomena in the stratosphere, and Peter Heinz and Peter Reed work a lot on these, how those external phenomena, those external oscillations, seasonal oscillation, can be coupled to the quasi-biennial oscillation and act as a pacemaker for the oscillations. And it's very interesting study of synchronization between external forcing and internally generated oscillations. And now I would like today to discuss something else, is what happens when you have multiple wave forcing. So first discussion occurred in a paper by Saravan, and then more recently, colleagues in Marseille, Pierre Léard, doing his PhD with Michael Lebars, observed that going back to our bifurcation diagram, they say, okay, but look, instead of taking a standing wave, we take a Gaussian distribution around these standing waves, and then they observe, perhaps surprisingly, that they came back to a periodic state. But then you could argue that because you remove some of the waves that generate the oscillation, you spread the amplitude, it's just as lowering the effective Reynolds number. So we went back into this problem to look into more detail about the mechanism. And here is an example of what happens when you get just two standing waves. So the base state is the same as before, the same QVO that was in a chaotic regime. And then there is a perturbation state. So there are four propagating waves, two standing waves. And what happens is that there is a kind of synchronization when the time scale of the, so independently, each of the pairs of waves would generate a QVO. A small scale QVO between those two values, or a large scale QVO between those two values. And when taken together, those two chaotic quasi-biennial oscillations becomes nearly periodic. So this is the observation, and we find it again puzzling. And I show you another example. Is the reverse case where the base state has a smaller phase speed than the perturbed states. And the dynamics is a bit different, but again, when the time scale of the descent of the front are of the same order, we recover nearly periodic states while we couple the two chaotic states. So here is the full phase diagram where we vary the ratio of the phase speed between the two standing waves. We vary the ratio of the amplitude between the base state. So at 0, there is only a single standing wave QVO with a base amplitude FB. And then little by little, we increase, we add. We do not remove anything, we add forcing. And by adding forcing, we recover periodic regimes. If it is too strong, we come back into a chaotic regime ruled by the perturbed waves. So there are really a huge region in parameter space where we recover periodic states just by considering multi-wave forcing. So this is important in the context of the interpretation of the Earth QVO because multiple kind of waves are observed there, equatorial, Kelvin, mixed Rossby gravity, or small-scale internal gravity waves. And those waves correspond to different parameters in terms of phase speed, frequency, wave number. And we hope to be able to guide some interpretation of the effect of those different waves with this model. So I will not have time to speak about this, but I will summarize the results for the question. So we observe bifurcation to our non-periodic solution in the Holton-Lindzen-Plumb model, and it persists in a more complex model than this quasi-linear model. Importantly, those chaotic states correspond to excitation of high vertical mode. Increasing the wave damping length scale favor periodicity. It's a simple observation, but maybe it matters to interpret the role of different kind of waves. And when you put multiple waves into the problem, you can have a resurgence of periodicity. And but the next steps now, we would like to come back to those events and to see if we can interpret them as the excitation of those high vertical mode, either temporary or in a permanent regime. So for this, I was quite interested by the talk of some of the biophysics talk. And then I would like to mention that there are many examples of such QBO-like oscillation on other planets, perhaps on the solar interior, I don't know. At least it has been speculated. And even on Earth, I showed you the QBO, but there is a semi-annual oscillation further up, which is synchronized, almost synchronized with the season. But how those two guys emerge together, I think it's not so clear. There are explanations for this, but it perhaps deserves to be looked again. So thanks for your attention.
Thank you very much. Questions? Thank you, first.
So I have two questions. First of all, just from crude estimates, you should be able to know values of gamma, coarsely estimate, say what frequencies of waves you get from convective storms. If you put those actual values into your model, would you get a roughly 2-year period? Reduce quantitatively?
Yeah, you get, when you, this number I took from Venaille's book, who took them from Andrew's book, I think. We took them from the original papers by Holton-Lindzen. So damping, yes, it's the time scale, it's 10 days maybe. Stratification, we know it. Stratosphere depth, we know it. The forcing is not so clear because which forcing should you take? The planetary waves, the small scale gravity wave, but those are going in different directions. So for this, there is a strong uncertainty. The viscosity is kind of eddy viscosity for turbulent motion, small scale turbulent motion in the stratosphere is not so clear, but the typical value taken are those one. The wavelengths, let's take the planetary wavelengths. Phase speed, this is well constrained. And it gives the right attenuation length scale. It gives a good order of magnitude over a year for the QBO. But then the Reynolds number can be anywhere here, I think. I think it's not so constrained. I don't think it's a problem of observation. It's a problem of the model be too simple. In the sense that to get the model, you need to estimate this. So I wouldn't be able to say if we are here, or here, frankly.
But in those ranges, is there a choice of parameters that gives you a 2-year cycle?
Yes. You can play with those parameters easily to get 2 years. Yes.
And if you don't mind, just a quick second question, especially because you put up that wavelength there. If you're talking about internal waves created by convective storms, I could imagine they're going almost equally leftward and rightward, except for the drift of the storms.
Yeah.
But if you're looking at planetary scale waves, effectively trapped equatorial waves, then there's a big difference between what goes westward and eastward.
Yeah.
And the question is, how robust is your model to changing the plus phase speeds and the minus phase speeds? You've had them equal in both cases.
Okay, so this issue was actually okay, the asymmetry was addressed in the early paper because the Holton-Lindzen considered not the small-scale gravity waves, but in their model before Plumb, they considered the Kelvin waves. Okay, it behaves as an internal gravity wave, and Yanai mixed Rossby gravity waves going in the other way. And but then the symmetry of the two waves is different, so I don't know if it is really the. And when you look at new estimate of the different waves, it seems that the Rossby waves that go westward play an important role. And if you look, then if you take, okay, it will change a little bit the expression of the model, but you can write out the model for the Rossby waves and for the Kelvin wave. And the phase speed will be different. Phase speed of Rossby wave will be smaller. The decay will be different, and it explains actually the asymmetry that is observed in the data. So you can get good rough estimate of the period, and you can understand the asymmetry of the forcing within the framework of this model. But then coming back to the first part of your second question, yes, small scale internal gravity waves are also very important, and a large part of the energy is within those waves. And in the recent estimates that try to say, okay, some part is in the planetary waves, which, as you say, confine the motion in the equatorial plane, and some part is in the small scale internal gravity waves. It seems to be half and half. So one is important to, it's my guess. One is important to set the large scale pattern, and the other is important to fuel the system. That would be my interpretation.
One very quick last question.
Is the main physical mechanism for dissipation in the stratosphere wave breaking of the gravity waves?
It's really a good point, because you can get this in the model. There is no wave breaking, but then you can play. And actually, we currently work on this to add a criterion for wave breaking, going back from a work by I think Johan Alexander and Tim Dunkerton, who have a parametrization for this, and we plug this parametrization in this model, and the results are quite surprising, interesting.
Okay, thank you very much.